Hey everyone. In this section, we're going to look at some of the various reactions that acids and bases can undergo. So the first one is the reaction of acids with metals. Okay, so I'm referencing something here called the activity series, okay, which is in your data book. We're going to go back to that more in the next chapter on electrochemistry. So take a look at it if you want, but we're not going to really study that in depth for a little bit. But for reactions with metals, metals found above hydrogen in the activity series will react with acids to form a salt and hydrogen gas. Okay, so if you see over to the right here in this video, um, the metal, when it's placed in a solution of acid, as it reacts, you can see the bubbles effervescing out of that. So that's the hydrogen gas that's being formed. You could do a hydrogen gas test by lighting a splint, a wooden splint on fire, to moving it above the hydrogen gas that's being formed. Hear a little pop sound if it is indeed hydrogen gas that you see. It's one way to test it. So a couple of different examples. We have hydrochloric acid and zinc will go to form the salt zinc chloride as well as hydrogen gas. Sulfuric acid and iron, we get the salt iron sulfate and hydrogen gas. And we have our acetic acid or ethanoic acid. And sodium will go to produce sodium ethanoate and hydrogen gas. So you can see that regardless of the acid and the metal, we always get the same product, a salt and pure hydrogen. Okay, now depending on what type of acid we have, if you remember in the last video, I mentioned there's strong and weak acids. So ethanoic in that last example is a weak acid, whereas hydrochloric is a strong acid. So depending on which acid you use, you can actually calculate the rate and study the rates of reactions as different acids and different metals will give off hydrogen at different rates. Okay, and that's according to the reactivity of the metal and the strength of the acid. So the next reaction is acids with carbonates. So carbonates you may be familiar with as antacids like Tums, or again the classic baking soda vinegar reaction is an acid with a carbonate compound. Okay, so metal carbonates and hydrogen carbonates react with acids to produce carbon dioxide and water and a salt. So you'll see in the video again, just like with the metal, we see the bubbles forming, but in this case, it's going to be carbon dioxide. So if we were to do a splint test on this one, we would see the flames start to go out a little bit due to being suffocated by the carbon dioxide gas. Okay, so a few examples here. We have hydrochloric acid plus sodium carbonate. Okay, and we see it forms our salt sodium chloride as well as carbon dioxide gas and water. We can have HCl plus sodium hydrogen carbonates. This is our hydrogen carbonates, the only difference, but we still form sodium chloride, carbon dioxide, and water. The only difference is because of the H here, we get a different ratio of how much salt we get formed. So this is you can do a test for carbon dioxide gas. So besides using a splint to distinguish it, all a splint really will do is distinguish between it being hydrogen or not, or oxygen. But you can pass carbon dioxide gas through a solution of lime water, which is calcium hydroxide, and the carbon dioxide will react with the lime, okay, creating a suspension of calcium carbonate, which is solid. So if you were to take this reaction down here, and if you were to attach a tube to it, collect the carbon dioxide gas and send it into a solution like this that containing calcium hydroxide, you would see a solid start to form, solid calcium carbonate that is insoluble in water. The next reaction we have is the reaction of acids with bases. So bases include metal oxides, metal hydroxides, ammonia compounds. Okay, there's a lot of different things which we can classify as a base. An alkali is specifically a base, but a base that's soluble in water. So not all bases are alkalis, but most of the ones we will be working with are. Okay, a reaction between an acid and a base, we call it neutralization. and it's so the resulting solution becomes more neutral than the initial one. So for example, if we take this base here and we add in some acid, so a base of pH 12, an acid of pH 2, we mix them together, we get a pH 8. Okay, so it's important to note that a neutralization reaction does not create a neutral solution. It's not necessarily going to be a pH of 7. The resulting solution will just be more neutral than the individual acid and base solutions before being mixed. Okay, and the resulting pH depends on the concentration of each. It depends on the volume, the amount of each that we have at the beginning. When undergoing neutralization reactions, we can tie this in with our thermochemistry unit by looking at the standard enthalpy change of neutralization. Okay, so this is the energy change. So when you react an acid and a base together to undergo neutralization, okay, it forms a salt and water. So this reaction is exothermic, so it will give off heat, meaning we have a negative delta H, and the enthalpy change associated with this is known as the enthalpy change of neutralization. Now it's specifically, and it's in bold here, it's the enthalpy change associated with the formation of 1 mole of water. So if we have more than 1 mole of water being formed, we have to alter our calculations a little bit to calculate this. So it's based on exactly 1 mole of water on the reaction of an acid and a base. Let's look at a few examples. So here we have hydrochloric acid and we have calcium hydroxide producing CaCl2, calcium chloride, and water. So in this case, we have 2 waters being formed, but remember the definition for neutralization is 1 mole of water. So we would actually, if we were to calculate the enthalpy, if we were to do the theoretical calculation for this one by using, say, the bond enthalpies or formation enthalpies, we would actually get double what it would need because we're calculating it for the formation of 2 moles of water. So we'd have to divide that answer by 2. Another example, sulfuric acid plus calcium oxide goes to calcium sulfate and water. Again, always forming a salt, so an ionic compound and water. And lastly, we have our ethanoic or acetic acid and our ammonium hydroxide going to ammonium ethanoate and water. This is our ionic compound. The CH3COO portion would be negative and the NH4 portion would be positive, creating an ionic compound. And of course, when we're dealing with things in solutions, not yet, it's the next slide. I mentioned that all of these things form a salt. So this is one of the important parts of an acid-base reaction is actually salt formation. Because we can produce salts on an industrial level and actually use these salts for various purposes. So sodium chloride, right? And it depends what salt we get depends on the acid and base that are reacting. For example, if we want sodium chloride, I'll write the reaction over here. We may take hydrochloric acid plus sodium hydroxide, okay, would produce sodium chloride and water. So if we took the correct amounts of each, we could produce a salt. We can then boil the water off, leaving us with the pure salt, which can then be sold or used, for example, as a food flavoring or food preservative. Some other salts that we can be produced depending on the acid and base reacting. We can produce potassium iodide, calcium chloride, potassium chloride, calcium carbonate, ammonium nitrate. And you can look over on the right for the uses of these. Now, all of these you've interacted with at some point in your lifetime. You just may not have known it. Potassium iodide is what's used in iodized salts. Okay, it's why we add it in to prevent iodine deficiency, to prevent thyroid problems. Calcium chloride is what we use when we throw ice on the roads or on our driveways in the wintertime to prevent the ice buildup. Okay, potassium chloride is just another, it's like sodium chloride, it's just a food additive. It uses potassium instead of sodium. Calcium carbonate is what's found in limestone and seashells. And ammonium nitrate is used in fertilizers. And it's also an active ingredient in cold packs. When you crack the cold packs, that's what makes it get cold, is a reaction of ammonium nitrate. Lastly, when we're dealing with anything in a solution form, and we're wondering about concentrations, we can of course perform titrations. So just a reminder of the titration process. So with an acid-base titration, we would take our alkali or our base, we add it to the burette. Make sure the top is closed. Okay, we would then fill up a conical flask. So we always want to do our titration in these. It prevents, so a conical flask, when we're dripping the base in, prevents things like splashing. It allows us to stir it around and mix it with our hands. Don't put your hands in it. I mean using your wrist to swirl the solution. And we have our indicator. So acids and bases are generally, the solutions of them are generally colorless, so they look just like water. So we do need an indicator to know when the reaction's finished. And we'll look at indicators more in the next unit. So these are all the pieces. So we have our base in our burette. We have our acid in our Erlenmeyer flask. We add a couple of drops of the indicator into our acid, and then we titrate. So for example, if this was phenolphthalein indicator, we would titrate, slowly releasing the amount of base into the solution of acid. Okay, and we know when it's reacted when the indicator changes color. So this is when the endpoint has been reached. We have a lower volume, we measure the base, and based on the amount added in, we can do things like calculate unknown concentrations, or calculate, if you remember back titrations, calculate things like antacid tablets, or different percentage masses of various acids and bases in different substances.